What if neural networks could learn not just when patients might experience an event, but how to trace the complex web of longitudinal signals leading up to it? Transformer-based survival analysis brings the power of self-attention mechanisms to time-to-event modeling, enabling us to integrate multimodal data, handle censoring rigorously, and uncover interpretable risk patterns across diverse clinical applications. Let's start by examining how transformers are adapted to model survival outcomes. Building on the architectural foundation, transformers for survival analysis leverage multi-head self-attention to model intricate relationships in patient data. Models like Former combine vision encoders for imaging patches with temporal transformers for longitudinal sequences, while Strafe applies self-attention over time-stamped health record visits, ultimately feeding into COX or discrete time hazard outputs. Moving to the loss functions, these models rigorously handle censored observations through well-established survival objectives adapted to deep architectures. COX partial likelihood ensures uncensored patients contribute log ratio terms, while censored individuals populate risk sets, and discrete time approaches model bind probabilities with careful treatment of competing risks through cause-specific hazards and reweighted estimation. Now we turn to how transformers integrate diverse and sequential data sources. Expanding on data integration, transformers naturally accommodate both longitudinal imaging sequences through vision encoders and irregular clinical event streams via temporal embeddings. On the multimodal side, models like TMSS and XSURV fuse imaging with genetic data using joint attention, while graph-based architectures capture spatial tissue organization at the cell and patch level for comprehensive risk modeling. Turning to interpretability, transformer models offer multiple pathways to clinical insight. Former and Strafe extract token-level attention saliency to identify influential time points and features, while occlusion experiments localize disease-associated anatomical regions, and integrated gradients on timestamped codes reveal both canonical cardiovascular signals and underappreciated long-horizon cancer risk markers. Let's examine the empirical benchmarks and real-world impact of these models. Empirically, transformer-based survival models consistently outperform prior approaches across diverse benchmarks. Former achieves C-index improvements exceeding 0.17 in neurodegenerative disease. TRA-CER sets new standards in competing risk scenarios with gains up to 0.2, and T-risk demonstrates robust generalization from UK to US health systems, while maintaining strong calibration at 36-month horizons. These advances translate to meaningful clinical deployment across neurology, oncology, and population health settings. Models are actively used for Alzheimer's progression forecasting with longitudinal imaging, multi-omic tumor survival prediction integrating pathology and genetics, and large-scale mortality risk stratification from electronic health records, alongside emerging non-clinical applications in sequential failure and retention modeling. Transformer-based survival analysis bridges deep sequence modeling and rigorous time-to-event statistics, delivering interpretable, calibrated predictions that integrate the full complexity of longitudinal patient journeys. To explore the latest research and implementations, visit emergentmind.com.